we find Q is nothing but the mass spin particles. But when it has principal mass, then V corresponds to massive gravity. Then this theory is the theory massive gravity coupled with massless gravity. And okay, 20 minutes. So okay.
I have
okay.
about 20 minutes.
Oh, okay. Then I just to talk about that so-called dark energy problem. Because this is the motivation why we consider the biometric gravity studies. Then just maybe today I finish only this part. Then the story is completely changed, but this is just a motivation why we consider biogravity studies. Anyway, you may but the observations of cosmic microwave background radiations ちょっとおかしいちょっと言ったきつ間違えたかないっかそういやメニュー分けましたSo yesterday you wrote the slide. Maybe that time I thought it could be more comprehensive, but something is missing. But anyway, recent observations on cosmic microwave background radiation tells that the universe is almost flat. Then the Human-Watson equations tell that the density in the parent universe could be given by axis. In case the special part of the universe is not flat, there appears some correction coming from the special curvature. But because the cosmic microwave background radiation, the observation of CMB tells that the universe is almost flat, then there is no term coming from the special curvature. Then the Human-Watson equation tells the energy density of the current universe is given by the Hubble constant H sub z, H. Then this quantity is 10 to the 29 gram per centimeters cube. And we often use the unit electron volt by putting Planck constant and mass density to the units. This quantities correspond to 10 to minus 3 electron volt for the phosphor and this quantities. This quantity not some C is called critical densities. Then anyway, we have flat universe. Rho is almost the energy density should be almost equal to the critical this quantities. But the density of usual matters, that is baryon, which makes planets and also the interstellar gas, is estimated to be 4.9% of the critical density. And we find from the rotational curve of the galaxy and also the behavior of the group galaxies, then there should exist dark matter. This should be almost 26.8% of quick density. Then there should be something unknown, which could be the 68.3% of the quick density. Then, yeah, we know this quantity very well, and we know this quantities, but it's not enough for the critical density. Then there should be exist something unknown. Then this could be called dark matter. Then this is just a graph of this critical density and usual matter, dark matter, and dark matter. Then and also before the observation type of the cosmic microwave background radiation, but observation of type 1A supernova. Type 1A is a kind of brightest supernova. The type of, and then by using type 1A supernovae, we found accelerating expansion starts about 5 billion years ago. And this is very, in some sense, very strange. By using the Fano equation, so I forgot to write explicitly. Anyway, ちょっと問題。A is called the scale factor. This is the expansion of the special part. Then if A is increasing functions, we call the universe is expanding. But second derivative of A is positive. Then we say the expanding is accelerating. Then we may consider this quantity, and this quantity can be by using the Einstein equation, or Itorabu equation. We look at this kind of equation. Here, rho is energy density in the universe, and P is pressure. Then, because the universe is expanding acceleratively, this quantity should be positive. But usually, energy density is positive. Then, because there is minus sign here, then P should be negative, and this quantity should become negative. Then, this tells that because we know that usual matter is the pressure of the usual matter can be neglected compared with energy density, because and of course dark matter is usually regarded as cold dark matter. Then the pressure is almost vanishes. Then this dark energy should have large negative pressure, even that there is accelerating expansion. So this tells that the dark energy should have a large negative pressure. We often use the quantity called the equation of state parameter. This is just the ratios P with respect to rho. P over W is given by P over rho. And several observations like CMB given by Dalmap, etc. The equation of state parameter corresponding dark energy should be almost -1. But as we know, radiation has, for the radiation, W should vanish, W is one side, because radiation is conformal. And in case of usual matter, and those called dark matters, they have their W vanishes. Because pressure is very small compared with rest energy, physical discount energy densities. And we know that cosmological constant is almost behaves as a fluid with W equal to -1. Then Laplace might be a cosmological constant. Anyway, if we consider the fluid whose EOS parameter, equation of step parameter W is constant, then this conservation of the energy density. This term coming from the expansion of the universe, because universe is expanding, then the energy density becomes decreased. And if the fluid has some pressures, the expansion makes some work. The energy density, some energy is lost. Then this, if P is positive, energy density decrease by the expansion. Then, but this if W is constant, P is just given by rho, W rho, W times rho. Then this term becomes 1 plus W rho times rho. And H is defined by the scale factor. That is 1 over A times dA dt. Then this equation can be easily integrated. Then we find this kind of expression. That is rho is proportional to minus 3 times 1 plus W. Now, if W is not equal to -1, and in this case, the rho is constant. Then, by using the Friedel-Larson equation, which is equation for the Friedel-Larson universe, given by the Einstein equations. In case of W is greater than -1, A is given by the power of P. And in case of this expression can be extended to the case of the W is less than -1, but this becomes negative. Then if P increases, A becomes decreased. Then we just slide the origin of the time like this. Then we obtain this expression in case of W equal -1. Then in this expression, if T is less than P naught, then this, if T increases, this quantity A is also increased, then this expresses expanding universe. But there is a singularities at T equal to T naught. This is called big group singularities. And in case A equal, W is exactly equal to -1, then in this case, A is, the scale factor A is proportional to expansion functions. And this is possible to so-called Dojita system.
No.
Yeah, because negative pressure is very unusual. If we consider the cube with size, the size of its size is L, like this. Each size becomes random by delta G, in this case. Then as I explained a little bit, the internal energy will decrease by the warp value expansions. If pressure is negative, this quantity is positive. Then the internal energy increases by the expansions. Then This is just some comment. The total energy is not conserved if we take into the reality. Actually, anyway. Also. Yeah, we need something. In case of W is greater than -1, but there occurs accelerating expansion. The corresponding fluid is called quintessence. That is fifth element. And in case W is less than -1, the fluid is called phantom. Then if there is a phantom in the universe, the density of the phantom increase by the expansion of the universe. So if the density of the phantom increase, the density of the density of the expansion also increases. Then if there is some phantom like this over here, yeah, the but expansions phantom grows and H decreases further, and the universe is fulfilled by phantoms, and finally the universe drift. This is big. Okay, yeah. 50. Right?
Maybe 10 for questions sometime.
Okay. Then there is something a little bit. Then maybe we finish today here.
Okay.
So. Yeah. Any questions? Sorry. Because, yeah. So.
So,
Yeah.
you would like to stop here?
Yeah.
Yes. So, now if you have some questions, it's time to make it. Please, questions.
Yeah.
That is one.
Quantum fields are usually bad for in physical point of view. And is this theory, is this problem solved?
Yeah. Yeah, the phantom if we realize the phantom by using the scalar field, for example, then the scalar field becomes a ghost. The ghost is inconsistent theory because in other quantum theories, it just generates negative noise. And but if we use, I will explain later. We may consider some kinds of modification of gravity, like FR gravity, or advanced ticket gravity, or gas bond, etc. Then we effectively obtain the phantom universe without introducing ghost. Then, if, in my opinion, if W is now observation test, W might be smaller than -1 a little bit. Might be, but not that could be some. But it might be changed. Anyway, so if really W is less than -1, then the ghost scalar field could be inconsistent. Then gravity should be modified. This is my opinion. Then, yeah. Then we are very interested in the value of the W as observations. If W is really less than -1, it is very interesting.
Are you satisfied? Any questions? Так что мы имеем время.
Yeah?
You have questions?
Historically, modifications of gravity have nothing to do with dark energy because they can well before. I mean, because at some point you say that the motivation for modifying gravity is dark energy, but even massive gravity is much older than.
My interest is in modified gravity in general. because as I explained, then we may explain the dark energy or accelerated expansion without any non-consistent fluid like a ghost field. Then we believe we consider several kinds of the modification of the gravities. But very recently, there is some great progress in the study of the massive gravity and the bigravity. Then we tried to use GS theory in order to explain the accelerated expansion. Okay.
Any questions? So we have a coffee break. Следующий доклад.